NGC 2440 is younger than the Eskimo Nebula and is actually, I do not think they've detected a hotter one yet. This one has the hottest known white dwarf stellar core. It's not totally a white dwarf yet. It's still developing into one, but it has a surface temperature of 200,000 Celsius. Here is another very interesting image, Hubble image of the same nebula. It may not look like it, but it really shows its bilobal symmetry in nature. Again, the mechanics of the collapse of white dwarfs in planetary nebula are different for every single situation and circumstance and still are not really well understood. Hines 2-248 is, this one is an image that was gotten by the Very Large Telescope high on an Andean mountain in Chile. This is, again, it is an optical image, and this is an artist illustration of the center of this particular planetary nebula. It actually has a pair of white dwarfs orbiting each other. Collectively together, they have a mass of about 1.76 solar masses, which exceeds Chandrasekhar's limit. And it is expected that in approximately 700 million years or so, that this might very well end up being a type 1a supernova event. If you are not familiar with white dwarfs, you know that stars themselves are kept in equilibrium by radiation pressure from the fusion process radiating outwards to the surface of the star, and that is counterbalancing the gravity, which is constantly trying to collapse the star. So as long as you have radiation pressure out and gravity in, then you have a happy star. As soon as it runs out of hydrogen fuel, though, and begins to collapse, then the core collapses. It gets even hotter inside. The next heavier atomic nuclei begin to fuse, radiation pressure again to push out, and these stars just keep expanding and contracting as they fuse heavier and heavier elements until they get up to carbon, or as you will see, carbon-oxygen, maybe even carbon-oxygen-magnesium in some cases. But when it gets to that point where it doesn't get hot enough for carbon or oxygen to fuse, then it collapses for the last time into a white dwarf. And in the process kind of sloughs off the outer atmospheric material, which now becomes the planetary nebula surrounding the white dwarf. And the white dwarf is now held in equilibrium because of Chandrasekhar's limit, which says that a white dwarf can only exist if it doesn't have any more mass than 1.4 solar masses. Now, there are super Chandra white dwarfs too, so it isn't exactly 1.4. It's somewhere around the vicinity of 1.4. But at that range, 1.4 solar masses, the electron clouds are right up against each other, repelling each other. We have electron degeneracy pressure that's stopping gravity from contracting this object any further. Now, when you have, so the electron degeneracy pressure is produced by degenerate matter. Every single possible bit of little space within that white dwarf is taken. There's not room in there for one itty-bitty tiny bit of anything ever. So if it tries to accumulate, if forces or circumstances, mechanics cause more mass to be added, so you start to approach Chandrasekhar's limit, then you have an instantaneous destruction of that white dwarf. So as long as you have that mass limit, then you have a white dwarf. Here's Hines 3-1357, the Stingray Nebula. This is the youngest known planetary nebula. And you can kind of see that because it's still very compact. There's still a lot of material right around the white dwarf. The winds haven't cleared out the debris from close to the white dwarf stellar core yet. Of course, it's not a white dwarf yet. It's working at it. It will be eventually. But you will see in sort of the 10 o'clock position another object, and that's the companion star. to the white dwarf in the middle. Now the Stingray is 18,000 light years away. So it looks like it's pretty small. However, it's very massive. It contains, it's about as large as 130 solar systems. So it is certainly quite large. It's a very complex structure. Again, they now think that these complex structures are formed because of companion stars with a white dwarf. So there are gazillions of stars out there. 2/3 of all those stars are in binary and multiple star systems. Therefore, there is billions of multiple systems that have a white dwarf in them. So you can have a white dwarf that has a companion that's a main sequence star, a red dwarf star, another white dwarf. There's all kinds of scenarios. But you need to have a companion star with a white dwarf that has to be close enough for contact to be made, that mass transfer can happen from one object to the white dwarf via an accretion disk that forms around the white dwarf in order to have some type of a type 1a supernova event. So let's go back to our little stellar evolution graphic where we have the scenario of protostar, sun-sized star, red giant, planetary nebula, and white dwarf. If you are not familiar yet with the HR diagram, and those of you who are just doing astronomy this year and you were in the B division last year, you had the HR diagram, so you're probably already familiar with it. Any of you who have not competed in a space science event for Science Olympiad yet might not be knowledgeable about the HR diagram, but you will by the time competition comes, because this is a really important graph for understanding stellar evolution. It is basically a plot of stellar evolution. As you can see, we have across the horizontal axes at the top is temperature, at the bottom is spectral class, the temperature of a star. The spectral classifications of stars are designated because of the temperature they have. So the temperature of a star is one physical property that's plotted on this diagram, along with absolute magnitude that you see on the left-hand vertical axis. The absolute magnitude is how bright the star actually is. Its intrinsic brightness, not its apparent brightness or how bright it appears to be from Earth, but its actual intrinsic brightness. If you took every single star in the sky and lined them up in one long row, 10 parsecs from Earth, you would see, for instance, the sun would be a +5, and when we look up at the night sky, the dimmest stars that we can see are about a +6, so you can see that the sun is really not a very, very bright star at all, rather mediocre in the brightness range. So the scale is a logarithmic scale. So the absolute magnitude scale works sort of like the pH scale does in chemistry, where the higher the negative number, the brighter the star, and the higher the positive number, the dimmer the star. So we have +15, very dim, up to -10, very, very bright. Also, you'll notice that unlike mathematical graphs that always start with the least amount at the origin and work their way increasing, going up and across, this one starts with the hottest stars at the origin, and then as you go across horizontally, you go from bright to dim. So O, B, A, F, G, K, M. O stars are really hot stars, massive stars. M stars are very cool stars. Luminosity, sometimes you see luminosity instead of absolute magnitude. That is an arbitrary scale completely. It's simply relative to the sun. We say the sun is one solar luminosity, and other stars are as more or less luminous than the sun. And so and luminosity is sort of a measure of the power, the energy that a star has. So in the upper left-hand corner, you have the brightest and the hottest objects. In the lower right-hand corner, you have the coolest and the dimmest. In the lower left-hand corner, you have very hot but very dim objects. And in the upper right-hand corner, you have stars that are very, very bright but very, very cool. And all stars that are fusing hydrogen to helium in their cores lay along the main sequence. When they start to evolve off that main sequence, they ended up, their combination of brightness and temperature changes, they're now plotted in a different location on the HR diagram. So we talk about stars moving on to a branch or off from the main sequence. They really don't go anywhere, you understand. We're just saying that now they're plotted in a different location because they're in a different stage of their evolutionary history. So once you plot a star on the HR diagram, you know you know its brightness, you know its chemical composition, you know its age, you know its mass, and you know where it's come from and where it's going to. So like the periodic table of the elements, this is sort of like the periodic table of the stars that tells you all the important information you need to know about a star. And right here in this area, between the main sequence and the giant branch, or red giant branch, it's sometimes referred to, is a strip where the stars evolve from the main sequence up through this region to get to the red giant branch, and that's called the Mira instability strip. And in that region of the HR diagram, that's where you have Mira variable stars. The stars that are evolving up through there, again, they run out of hydrogen. The next thing they fuse is helium, and then they puff up, and then they collapse, and then they create through nuclear synthesis the next heavier atomic nuclei. They puff out, they collapse, they keep going over through that process, expanding and contracting, and they actually pulsate, and they change their brightness as they get larger and smaller. Their brightness changes, and if you plot that change in brightness over time, you have this curve called the light curve, and it shows you the behavior. These Mira instability strip stars, the Mira variable stars, have a period that's not periodic, but it's fairly periodic. And it ranges anywhere from 300 days to a year that it pulsates back and forth as it's moving through this instability region on its way to becoming a full-fledged red giant.